Together, let's walk the path of knowledge, step by step, lens by lens, towards a clearer understanding of physics of light. So, tune in, stay curious, and let's begin this illuminating journey. Whether you are a student, a science enthusiast, or simply curious about how light shapes our perception of universe, this podcast will break down complex ideas into clear, insightful discussions. Join me as we explore the principles of reflection, refraction, lenses, mirrors, and intricate workings of optical instruments that power everything from microscopes to telescopes. Welcome to the Walking Clearwater, a podcast where we illuminate the depths of physics one concept at a time. I am VB Kataria, and in this series, we embark on a journey through the fascinating world of ray optics and optical instruments. Welcome to the Walking Clearwater podcast. So, let's dive in to basic concepts of and learn the basic concepts of ray optics and optical instruments. Number one, optics. The study of nature and propagation of light is called optics. Ray optics deals with particle nature of light, whereas wave optics deals with light as a wave. They consider light as a wave. Two, reflection of light. When a light ray incident on a smooth surface bounces back to the same medium, it is called reflection of light. Laws of regular reflection. First is angle of incidence is equal to angle of reflection, i.e., I is equal to R. Number two, the incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. These laws hold for any reflecting surface, whether plane or curved. There is no change in wavelength and frequency during reflection. Spherical mirror. A spherical mirror is simply a part cut off from surface of a hollow sphere which has been made smooth and silver polished on one side. Spherical mirrors are of two types. First is concave mirror. If outer side or bulging side of the spherical mirror is silver polished, it is called concave mirror. Second is convex mirror. If inner side of spherical surface is polished, it is called a convex mirror. Relation between focal length and radius of curvature. The distance between center C of spherical surface and its pole P is called the radius of curvature. It is denoted by R. The rays parallel to principal axis CP after striking the mirror meet at a point F in concave mirror or appear to be meeting at a point F in convex mirror. This point is called the principal focus of mirror. The distance of focus F from pole P of a mirror is called focal length of the mirror. It is denoted by F. The focal length F is half of the radius of curvature. F is equal to R by 2. Mirror formula. The mirror formula is 1 by f is equal to 1 by v plus 1 by u, where u is distance of object from mirror, v is distance of image from mirror, f is focal length of mirror. Magnification produced by mirror. The ratio of size of image to the size of object is called the linear magnification produced by the mirror. Magnification m is equal to h dash by h is equal to minus v by u is equal to minus f upon u minus f is equal to f minus v by f, where h dash is the height of image and h is the height of object. Refraction of light, a new topic. When a ray of light enters from one transparent medium to another, there is change in speed and direction of the ray is the second medium. In the second medium, this phenomenon is called refraction of light. Laws of refraction. The incident ray, the refracted ray, and the normal to the surface spreading and separating the two media all lie in the same plane. Second, Snell's law. For two media, the ratio of sine of angle of sine, okay, SINE, of angle of incidence to the sine of the angle of refraction is constant for a beam of particular wavelength, i.e. sine I by sine R is equal to constant is equal to N2 by N1 is 1 and is equal to 1 and 2, and where N1 and N2 are absolute refractive indices of first and second media, respectively, and 1 and 2 is a refractive index of second medium with respect to first medium. Due to principle of reversibility of light, sin R by sin I is equal to 2 and 1, and multiplying the first equation sin I by sin R with sin R by sin I, we get 1 is equal to 2 and 1 into 1 and 2, or 2 and 1 is the reciprocal of 1 and 2. So that's the result we get from there, multiplying that both equations. The frequency of light remains unchanged while passing from one medium to another. And refractive index, moving on to that, the refractive index of medium is defined as the ratio of speed of light in vacuum to the speed of light in medium. N is equal to speed of light in vacuum by speed of light in medium is equal to C by V, is equal to nu lambda of air by nu lambda of medium is equal to lambda of air by lambda of medium. Lambda air and lambda medium are wavelengths of light in air and medium respectively. So from here we can say that sin I by sin R is equal to N2 by N1 is equal to C by V2 by C by V1 is equal to V1 by V2 is equal to lambda 1 by lambda 2. Formation of image due to refraction. According to Snell's law, N2 greater if N2 is greater than N1, so then I is greater than R. That is, if a ray of light enters from rarer medium to denser medium, it is deviated towards the normal. And if N2 is less than N1, I is less than R. That is, if the ray of light enters from a denser to a rarer medium, it's deviated away from the normal. Accordingly, if the ray of light starting from object O in the given diagram, there is a glass slab. Consider a glass slab, okay? In whatever textbook you have, you might be having a glass slab, okay? So, whenever ray enters from air into the glass slab, the light ray it will be bending towards the normal, and when a light goes from the glass slab to air, which is denser to rarer, the light ray will bend away from the normal. So um, we can have name another variable as small n is equal to real depth, which is the total, like the depth of the glass slab, the thickness, whatever it had to cover, divided by apparent depth, which is mi. Let's say mi is equal to t by t minus x. So where x is the apparent shift, the apparent shift, it is the whenever we, let's say that a light ray is going from the glass slab to air. So at the point the interference, the light ray will be bending, and if we trace the bended light ray which is now in the air back into the glass slab, if we trace it, then the point where it intersects the point from where the light ray started from the glass slab, all right, we call that thing as an apparent shift. So the apparent shift is 1 minus 1 by n into t, which is the refractive index n, and t is the thickness. So in that way you can find the apparent shift of the glass slab, the amount of the shift happened as the light ray bends and it changed its path. All right, moving on. Refraction through a number of media. Let us consider the refraction of light ray through a series of media as shown in figure. The ray AB is incident on interference at angle I, let's say, and the ray is deviated in the water along BC towards the normal. Then it falls on water glass interface and is deviated again towards the normal CD. If the last medium is again air, the ray emerges parallel to the incident ray. Let R1 and R2 be angles of refraction in water and glass respectively. Then from Snell's law, we can say sin I by R1, which is air to water, is N water by N air is equal to A and W, let's say, and which is refractive index of water with respect to air. A and W is denoted by that. And sine R1 by R2 is from water to glass. It is N glass by N water is equal to W and G. And likewise, sine R2 by sine I is glass to air again. Na by Ng is equal to Gna. So multiplying the equation of sine I by sine R1 and basically all of the three, if we multiply them, we get the product as 1. So by that we can conclude that let's take that refractive index of glass with respect to water, it will be equal to 1 by refractive index of water with respect to air multiplied by refractive index of air with respect to glass, which is equal to refractive index of glass with respect to air divided by refractive index of water with respect to air. So that's the relation if there are three mediums and a light ray is passing through three of them. So in that way, we can come to know about this. Then we talk about critical angle. When a ray of light is incident on interface from denser medium to rarer medium, it is deviated away from the normal. When angle of incidence is increased, angle of refraction also increases and it becomes 90 degree. The angle of incidence in denser medium for which the angle of refraction in rarer medium is 90 degree is called the critical angle. See pair of media. If Nr and Nd are refractive indices of rarer and denser media, sin I by sin R is equal to N2 by N1 gives sin C by sin 90 is equal to Nr by Nd is uh, sin C is equal to dNr is equal to 1 by R and D is equal to 1 by N. We know the relations. And as we had seen the reciprocals and all of that. Now the total internal reflection. When angle of incidence in the denser medium is greater than the critical angle and the incident ray does not refract into rarer medium but is reflected back into the denser medium, this phenomenon is called the total internal reflection. This condition for internal refraction are the ray must travel from denser to rarer medium, and the second is the angle of incidence I should be greater than the critical angle C. So then the total TIR happens. Critical angle for water, air, glass air, and diamond air interfaces are 49 degree, 42 degree, and 24 degree respectively. Spherical lenses is the next topic. There are two types of spherical lenses. There are two types of spherical lenses, convex lens and concave lens. Concave is known as diverging and convex is known as converging. Rules of image formation. The first rule is the ray incident on the lens parallel to the principal axis after refraction through the lens passes through the second focus or appear to come from second focus in concave lens. Second is the ray incident on lens through optical center C after refraction pass straight without any deviation. Third is a ray directed towards the first focus incident on the lens after refraction becomes parallel to the principal axis. 7. Thin lens formula. If U and V are object and image distances from a lens of focal length f, then the lens formula is 1 by f is equal to 1 by V minus 1 by U. This equation holds for convex and concave lens both, but proper signs of U, V, and F are to be taken used according to the sign convention of coordinate geometry. Focal length of a convex lens is taken as positive and the concave lens is taken as negative. Magnification produced by a lens M is equal to H dash by H is equal to V by U is equal to F by U plus F, where H dash is, we know that, and H dash is the size of image and H is the size of object, we know that, and lens maker's formula is the next topic, which is if R1 and R2 are the radii of curvature of first and second refracting surfaces of thin lens of focal length f, then the lens maker's formula is 1 by f is equal to 1 and 2 minus 1 into 1 by R1 minus 1 by R2. It can be also written as n minus 1 into 1 by R1 minus 1 by R2, where 1 and 2 is equal to n is the refractive index of material of lens with respect to surrounding medium. Alright, then there is another topic which is power of lens. The power of a lens is ability to deviate the rays towards its principal axis. It is defined as the reciprocal of focal length in meters. Power P is equal to 1 by F in meter. Its unit is diopter and is represented as capital D. Lens immersed in a liquid. If a lens of refractive index Ng is immersed in a liquid of refractive index NL, then its focal length FL in liquid is given by 1 by FL is equal to refractive index of glass with respect to liquid, which is LNG minus 1 into 1 by R1 minus 1 by R2, where LNG is equal to Ng by NL. If Fa is the focal length of lens in air, then Fl is equal to Ng minus 1 by Ng into N, which is F1. Fl is equal to Ng minus 1 into Fa by Ng by NL minus 1. Three cases. If Ng is greater than NL, then the Fl and Fa are of same sign, but Fl is greater than Fa. That is, the nature of lens remains unchanged, but its focal length increases and hence the power of the lens decreases. In the other words, the convergent lens becomes less convergent and divergent becomes less divergent. If Ng is equal to NL, then FL is equal to infinity. That is, the lens behave as the glass plate. If Ng is less than NL, then FL and FA have opposite signs. That is, the nature of lens changes. A convergent lens becomes divergent and vice versa. Thin lenses in contact. If two or more lenses of focal length f1 and f2 are placed in contact, then the equivalent focal length f is given by 1 by f is equal to 1 by f1 minus 1 by plus 1 by f1 plus 1 by f2 and so on. Power of combination is p is equal to p1 plus p2 and so on. 12. Combination of lens and a mirror. Consider a coaxial arrangement of lens and mirror. Let an object be placed in front of the lens. The incident rays from the object first undergo refraction at lens and are then incident on the mirror. To obtain the position of lens due to combination, we can proceed as follows. 1. Using refraction formula, we can calculate we can calculate where the image would have been formed had there been only the lens. We then consider image as an object for the mirror. 2 is using mirror formula. We can locate the position of its final image formed by the mirror. This final position would be position of image due to combined effect of refraction at the lens and the reflection at the mirror. 13 is refraction through a prism. A prism is a transparent medium enclosed by two plane surfaces. um, let's let EF be the monochromatic incident ray on the face PQ of prism PQR. If refracting angle A at an angle difference I1, this ray is refracted along FG, R1 being the angle of refraction. The ray FG is incident on the face PR at the angle of incidence R2 and is refracted in air as GH. Thus, GH is the emergent ray and I2 is the angle of emergence. The angle between incident ray EF and the emergent ray GH is called angle of deviation delta. For a prism, if A is refracting angle of prism, then R1 plus R2 is equal to A. I1 plus I2 is equal to A plus delta. Clearly, deviation delta is I1 plus I2 minus A, where I1 and I2 may be interchanged. Therefore, there are two values of angle of incidence for same deviation delta. If n is refractive index of material of prism, then from Snell's law, n is equal to sine I1 by sine R1 is equal to sine I2 by sine R2. And we also have to remember a graph which tells the relation between incidence and the deviation angle. So yeah, that is also an important graph over there. If you have any textbook, you can look it or in that textbook. And let me just show you that thing, for your convenience. And yes, that is that thing. And this is another one, the prism. Yes. And now minimum deviation. At minimum deviation, the refracted ray with a prism is parallel to the base. Therefore, I1 is equal to I2. Let's say R1 is equal to R2. That also let us assume. Then from equations which are R1 plus R2 is equal to A and I1 plus I2 is equal to A plus delta. We can say that R plus R is equal to A, or R is equal to A by 2. I plus I is equal to A plus delta, or I is equal to A plus delta M by 2. Delta M is the minimum angle of deviation, minimum deviation angle. And the refractive index of material of prism N is equal to sin I by sin R is equal to sin A plus delta M by 2 whole divided by sin A by 2. So in that way, we find the refractive index of material prism if we have the minimum deviation, or we can find like any variable we want to find from that. For a thin prism, if the thin prisms are the ones which have angle of the prism less than equal to 10, in that delta m is equal to n minus 1 into angle of prism. Next topic is scattering of light. The light is scattered by air molecules. According to Lord Rayleigh, the intensity of scattered light I is inversely proportional to 1 by wavelength raised to power 4, as lambda blue is less than lambda red. Accordingly, blue color is scattered the most and red is scattered the least, so sky appears blue. At the time of sunrise and sunset, blue color is scattered the most and red color enters our eyes. So sunrise and sunset appears red. 15 is optical instruments, microscopes and telescopes. A microscope is an optical instrument used to see very small objects. Number one. First is simple microscope. It consists of only convex lens of small focal length. If beta is equal to angle subtended by an image on eye and alpha is angle subtended by object on eye, when object is at distance of distinct vision, capital D, magnifying power m is equal to beta by alpha is equal to capital D by V into 1 plus V by F. Final image is at infinity, where V is equal to infinity, then M magnification is equal to capital D by F. The final image is at distance of, if the final image is at distance of distinct vision, V is equal to D and M is equal to 1 plus D by F. Compound microscope. A compound microscope essentially consists of two coaxial convex lenses of small focal lengths. The lens facing the object is an objective lens, while towards the eye is called the eye lens or eyepiece. Magnifying power of microscope M is equal to beta by alpha is equal to MO into ME. Both of the multiplication of them, MO and ME, is equal to V naught into capital D by U naught into VE into whole multiplied by 1 plus VE by FE. And the astronomical telescope or refracting telescope, it is used to see magnified images of distant objects. An astronomical telescope essentially consists of two coaxial convex lenses. The lens facing the object has large focal length and the large aperture and is called objective, while lens towards the eye has small focal length and small aperture called eye lens. See, first is called the objective, all right, and second is the eye lens. Magnifying power of this telescope is angle subtended by final image at eye whole divided by angle subtended by object on eye. It is beta by alpha basically, which is m object into me is equal to minus f naught by fo by fe divided, which is minus f object by fe into 1 plus fe by ve whole multiplied by, all right, it is in bracket. And here is the formula. You can see this one. This is the astronomical telescope one formula of magnification. and where UE is equal to distance of real image from eye lens, VE is equal to distance of final image A dash B dash from eye lens, and F naught is equal to focal length of objective, FE is equal to focal length of eye lens. Alpha is angle subtended by object at I is equal to h by f naught FO, and object which is objective lens, and angle subtended by image at lens is equal to h by FE. Now, moving on to the reflecting telescope. In this telescope, a concave mirror is used as objective in place of convex lens. It is free from chromatic aberration, and it has larger resolving power than refracting telescope. So, astronomical telescope is known as refractive telescope also, and the reflecting telescope uses concave mirror instead of an objective. And in astronomical telescope, the objective is convex lens, but here we in reflecting telescope we use concave mirror, and it has a larger resolving power than the astronomical telescope. Now, the last topic is magnifying power of optical instruments. The size of an object depends on the size angle subtended by object on eye. The angle is called visual angle. Greater the visual angle, greater the size of object. Stars are bigger than the sun, but appear smaller because stars are much farther away from the sun, and they subtend smaller angles on eye. The angle subtended on eye may be increased by using telescope and microscope. The telescope and microscope form image of an object. The image subtends larger angle on eye, hence the object appears big. The magnification produced by optical instrument, telescope or microscope is defined as the ratio of angle beta subtended by image on eye and angle alpha subtended by object on eye. Angular magnification m is equal to beta by alpha. So yes, that was for this chapter, and thank you for attending this podcast, and stay tuned for many other chapters which we are going to cover. So thank you everyone.